So today, I'm going to be talking about some work that was done at UMass. I am also affiliated with Amazon, but today I will be speaking as a UMass professor, giving my personal views. So I'm going to be talking about accelerating software development, the LLM revolution. So I wonder how many of you are familiar with this event, the Cretaceous Paleogene extinction event. Like, raise your hand. All right. So that's a good number. So for those of you who aren't aware, it's when this giant chunk of rock came crashing down on the Earth and brought a lot of changes that were maybe not actually welcomed by the dinosaurs. So one thing I noticed recently about these meteors coming down is that they bear a strong, striking resemblance to some LLM providers. And these dinosaurs, when I'm depicting these dinosaurs here, I mean traditional software development tools, all right? And so we have this kind of mass extinction event that is occurring. But these extinctions open up new opportunities, right? New niches in the ecology. So maybe we're going to move away from dinosaurs and end up with these little guys. So this talk is structured around what I think is a pretty effective recipe for evolving software development tools and just getting a whole new breed of these tools. So it consists of 3 parts. The first is evolve. So we're going to evolve the tool in a way that actually closes the loop between what the tool provides and what developers actually want. And this will become more clear very, very soon, what I mean. Right? In essence, what I mean is tool plus plus. Not to be confused with C++. Then we're going to exploit the niche, right? So the niche here means the developer tool that we're enhancing, that we're evolving, has access to some information. This information is actually super valuable for an AI to actually guide the effectiveness of the AI and make it work. And then finally, ensuring fitness. Right, so you have this evolved creature, and this creature is fitting in, but is it actually fit? And the way that we're going to fit is we're going to make sure that what the AI produces actually is correct in some way. So we'll have some validation in the loop. And in particular, I'm advocating a strategy that is really evolutionary, a little revolutionary. The first is, okay, yes, these dinosaurs of dynamic and static analysis, the dinosaurs didn't actually die out. Right? Like, they're flying around us all the time, right? Dinosaurs actually continue, and they're kind of cool. And so these dinosaurs, like dynamic and static analysis, these things that we've relied on as workhorses for years and years, are still absolutely valuable. So what are some characteristics of them? We're quite familiar with these characteristics, right? They tend to be deterministic. They allow sound and precise reasoning over restricted domains of logic, for example. And at the end of the day, you get ground truth out of these tools, right? With LLMs, the story is a little bit different, right? So LLMs are pretty stochastic, but they go beyond sort of first order logic or something like this. They can actually bring in domain understanding, right? So, let me stress, by the way, I'm going to anthropomorphize the hell out of LLMs during this talk. So do I think they're people? No, I do not think they're people. But I am going to use this as a device. So when the LLM decides, the LLM understands, and so on. Dijkstra is spinning at 4,000 RPM in his grave right now. Let's characterize what they do as heuristic. Right? So they provide responses. These responses are not grounded in logic, but they nonetheless have a lot of value. So I'm arguing that we should have the best of both worlds, try to mitigate the problems of each while enhancing something and getting a mixture that's better than the sum of its parts. All right, so during this talk, I'm going to be presenting a kind of whirlwind view of a number of the tools that we've developed in our lab that are all examples of this sort of strategy of taking existing developer tools and enhancing them by integrating AI into them. So there's a profiler ++, coverage analyzer ++, debugger ++, compiler ++, and notebook ++. So that's the broad overview. So first I'm going to talk about scaling. So as Denise mentioned, scaling is a system from our lab. I actually presented it 2 years ago at this very exact location. Anyway, it's a great paper. It's a great tool. It is a profiler for Python. It has some interesting characteristics I'm not going to go into detail about. It allows a fine-grained breakdown of whether your code is spending a lot of its time in the Python interpreter, which is bad because the Python interpreter is slow, or whether it's running in native code, which obviously is the ideal. So it helps you steer your code to become more performant by using native code instead of Python. But Scalene, after the paper actually got accepted, we decided to integrate AI. And so what we have now are these AI optimization options. So you can go ahead and say, it's a bring your own key situation, and you can say, I want certain kinds of proposed optimizations. And when you click on a little explosion button, it's a little hard to see, it will go and ask the AI for a proposed optimization of your code. And these optimizations, the text is hard to read, but it's got an explanation of what the optimization is and why it should do better. And the performance improvements can be pretty stark. So this is an example of an AI-generated optimization that sped up some code by 90x. Right? And 90x seems crazy, but it's a little bit the order of the day with Python because Python is so much slower than native code. Getting this kind of speed up is possible, and the AI is able to effectively provide these suggestions. So what did we do here? So we took a profiler and we extended it, and we made a profiler that suggests optimizations. So I argue that this is really closing the loop between the tool and the human's goal. No one really wants to use a profiler. They just want their code to be fast, right? So the profiler is, people are like, oh, I want high performance, I use a profiler. Right, but it's sort of like, I would like to go to a concert, I need a key for a car. Like, yes, that is true. It will get you part of the way there, but it's not going to get you the whole journey. So here, past profilers are really tools that show you, at best, in general, here's some place your code is maybe slow or it's consuming too much memory. You figure it out. So it's better than nothing, for sure. But here, by integrating AI, Scalene is actually telling you, oh, I figured out where your code could be more efficient, and now I will suggest optimizations for you. Right? So why is the profiler able to do this where, like throwing it into ChatGPT maybe is not so good? So first, if you have a giant code base, the profiler narrows down where your attention should be and where the AI's attention should be. If you just take a giant code base and throw it over the fence to an AI, the AI is not actually going to produce very good results at all. In addition, the profiler doesn't just know where the code is inefficient, it knows why it's inefficient. Right? It has detailed information about, like, this thing is using a GPU, this thing is running in the interpreter, and so on. So for example, if you're spending a lot of time in the interpreter, the right thing to do, as I said before, is to switch to using native libraries. If your utilization of cores is low, you have 64 cores on your machine, and your core utilization is 1/64th, obvious problem, right? Your code needs to be parallelized. So you can have the AI be directed, oh, the thing that I want you to do here is to vectorize this code, or make it multi-threaded, or use multiple processes. If this is actually something that happens a lot, you get no or poor usage of a GPU or other accelerator, then you can say, look, why don't you use some GPU-optimized libraries? All right? So now we have some sort of optimization suggestions, and we would like to make sure that they're at least somewhat correct. So one nice thing about profiling, and for this particular use case, is you have the original code. And the original code is an oracle. That's what you want the new code to do, right? Just faster and better. So you can make a loop where you actually go ahead and compare the code and the code results to the original via testing or via generating, well, let's say different examples and verifying that these things work. In the limit, it would be lovely to be able to prove these things equivalent. That's currently out of reach for general purpose Python programs, but maybe we're getting there. Also, of course, you want to validate that the suggestion does what it's supposed to do, that is optimize the code. Right? So fitting into this template, we've got an evolve tool. It's a profiler ++. It suggests code optimizations. It exploits its niche. The profiler knows not just about the static characteristics of your code, but it has detailed, fine-grained performance information that it can use to guide the LLM to actually generate code that solves the particular performance issues. And finally, you can ensure fitness. You can actually verify that the code is still doing what the original code does. All right? OK, so on to some tools that I have not actually discussed on this stage. So these next things are all fresh out of our lab. So this one is ChatDBG. It's evolving a new debugger. This is joint work with a number of folks. We just presented it at FSE 2025 in Norway. So debuggers. Debuggers are great and terrible. So this is a screenshot of a real debugger. There's all kinds of tools. It's not, it's like, OK, I can see a stack. I can see some symbols. Now go figure out what's wrong with your program. It gets worse. If you're using a Python notebook, for example, or you're using a command line interface in general, you're kind of left in this situation where you just get a prompt and a blinking block. And so what do you do next is dependent on the ability of the programmer. Well, I've taught a bunch of computer scientists, and the number of them who actually use debuggers is very, very low. This seems to be a common theme. So I visited Reddit, and Reddit was basically like full of comments like this. Like, is the debugger really useful? I have been developing games in Unity for about 2 to 3 years, and I never, and I say never, used a debugger. Pride, all right? I find them useless. It lets you walk step by step. I honestly have no clue how to even use them. And I survived years by not using it. So of course I use, debug print to see how they, so they don't use debuggers, right? Debugger, I don't even know what to do. What do you guys think of debuggers? My boss just implied he might force me to use a debugger one of these days. This is obviously workplace harassment. Right? My favorite is, I think it's more of a destructive habit than anything. Here's another one, somebody who actually has some experience with debuggers and said, hey, why aren't you all using debuggers? And this team of developers said, why not try using print statements? So you have to feel sad for these folks, right? They want to actually get their programs to run correctly. They have bugs, right? But they find themselves in this situation where they can't, the debuggers don't help. Right? Print statements are better for them than debuggers. So why? Why is this the case? So debuggers have existed for quite some time, but amazingly, their feature set is basically the same at minimum since the 90s. So if you look at this chart, you can see that GDB in 1986 had basically all of the features except one tiny feature that they added in 91. Right? This is a long time ago. Right? Nothing has happened. It's like LLDB is the state-of-the-art debugger, and it does basically the same thing as PDB or GDB. So this is pretty grim. So this is why we created ChatDBG. It has a bunch of new features. I'm going to walk you through a demo of ChatDBG and then talk a bit about how it works. All right? So here we have a Python program, and it has failed. It comes up with an assertion. It says, oh, the length of stats it should equal num trials, but it doesn't. This is taken from student code for a data science class. And so in ChatDBG, you can actually issue different kinds of commands, including just why. Why? So you can use much more directed commands, but why is actually good enough to get going. And so here, all of the stuff in color is ChatDBG actually running the debugger itself. So everything you see here, like the command where it says info bootstrap statistic, was issued by the LLM. And so it's running the debugger to get information. It walks up and down the stack, prints out values of various variables, and then comes to a conclusion about what the root cause of the error is and suggests a fix. And in this case, the fix is indeed correct. All right? So what's happening here? So normally, right, you interact with the debugger. There's just some debugger like LLDB, and you enter commands or you click buttons in the user interface. And here with ChatDBG, we extend this with an agent that actually intercepts all of the PDB or GDB commands and then sends them off to the LLM. So the first thing it does is it creates this enriched stack. And this is leveraging dynamic information that the debugger has that's not present in the code. So rather than just saying, oh, here's whatever stack frame we have, we skip library code because the assumption is the person who's debugging is not trying to debug the system's libraries. We increase the context, so it's not just like the one line responsible for each frame. We add information like global variables, what the type of the variables are, right? A lot more information that makes it more useful to the LLM to actually bootstrap this process of getting some debugging happening, all right? Once it has this in hand, it sends the prompt off to the LLM, and then the LLM actually takes over, right? So here, the LLM can now issue commands that get executed on the client side by the debugger itself. So it can run, straightforward debug commands like print a value, which is something the LLM might do. But we've also extended its functionality. So, debuggers, like moving around in debugger and going up and down frames and stuff is fine, but actually trying to understand code this way can be really hard, as those of you who have actually used debuggers and not just print statements could attest to. So what we've extended, the debugger functionality, we've extended with a language server. So there's, for C and C++ code, we have this ClangD tool that is this well-known language server that allows the LLM to invoke functions like just give me the code surrounding this line, or look up the definition for the first occurrence of this symbol. So this is way, way more effective than just having the LLM walk around the code blindly, trying to figure out what on earth this definition, like where it was defined. We can go straight to the definition of the code. We also have a similar server that we created for Python that allows you to look up information about a symbol just by saying info symbol. And then for Jupyter Notebooks, this is really a crucial piece for notebooks, we compute a backward slice of the symbol. So we can actually get all the source code that leads to this value of a symbol, which is important because Jupyter Notebooks can break up throughout their flow different order of execution. So you have like a bunch of cells, but you really just want the cells that correspond to the result that you're seeing. So you probably are asking yourselves, Emery, does this seem like a good idea to open up like a socket to an LLM to let it like run code in my client? I'm uncomfortable with that. And maybe you should be uncomfortable with that, right? It's a little scary. I will say we've not yet had any malicious activity come out of an LLM, but that doesn't mean it's not going to happen. And so we have a straightforward approach to deal with this problem. We use container as a sandbox, and we whitelist commands. So it turns out that debuggers can actually execute arbitrary code. Who knew? Like everything. And so we make it so that the debugger can't actually execute those commands. So even if the LLM were like, I would like to execute system rm-rf/, we will say, no, thank you very much. All right? OK, so how does it work? It works out pretty well in practice. So we basically compared this to running just like ChatGPT. I've got an error. Let's see if ChatGPT can figure it out. The success rate of this is pretty low. It actually solves some problems, but it's under 25%. Adding the enriched stack and then just saying why already bumps up the success rate to over 60%. All right? And so here's an example command being executed, right? Info proportion blue. Having a more targeted question, usually like just a straightforward, wait, why is this assertion? Why is this value not equal to this? Why is this a null pointer, which should point to an integer? It further increases the success rate. And if you continue this dialogue with the human, you achieve success rates north of 75%, nearly 80%. So what did we do? Again, fitting with this template. Like, no one wants to use a debugger. This is clearly true. People really don't like using them. Why? Because they're not solving their problem, right? The problem is they want to know what went wrong and what the fix is. And so that's this evolve tool. It exploits the niche here, right? The debugger has access not just to your source code, but to all this dynamic state. And this LLM, by having this world understanding, can actually reason about your code. So I did not reason about your code in a domain-specific way. So I didn't go into this in the example. But in the example and in our experience, we actually have had these interesting results where the bug is a semantic bug. Right? It's not like, oh, you did something wrong. It's like, oh, you said that you wanted to compute the proportion of blue marbles. That's what the function name is. That's not what's happening. Or you're running a bootstrap here, but you can't run bootstrap with just 10 runs. 10 trials of bootstrap is not enough. We should see thousands of trials. Right? So this is a kind of bug that's entirely out of reach for traditional debuggers that actually is now within reach with ChatDBG. And finally, of course, you obviously want to validate these things. There's a number of ways you can do this. You could patch the code. You can restart it, obviously run it through CI, et cetera. All right. Now I'm going to talk about CY. So CY, a number of these tools are really dear to my heart. This one is definitely dear to my heart. So it's evolving a new C compiler, or a new compiler. So it really is, the problem here is when you compile your code, sometimes it doesn't compile. And it's often not great. So if you've ever programmed in C++, this may have been your experience. I like this. It's somewhat tragic. I'm very new to C++, and I find it extremely hard to interpret the errors thrown by the compiler. I love that there's a question mark at the end. How do I interpret C++ errors? It shows pages of errors, which I don't think is human readable. I don't understand a single word in it. So the funny part about this Reddit post is it says that it's solved. Your laughter is appropriate. I was like, wait, solved? This problem is solved? How is it solved? So I decided to compile some code. So I took the latest version of Clang, and I compiled this code, and then this happened. Right? And so I don't think this is solved. This feels very unsolved. So by contrast, when you use CY, CY actually tells you in clear English what went wrong. And this is an accurate diagnosis. It says the problem is you're attempting to use std unordered set with std pair, but the standard library does not provide a hash function specialization for std pair. This is a great error message, right? That's the problem. But not only that, it says, oh, here's how you fix it. Here's a suggested hash function, right? And then here's the invocation. And now your problem goes away. And it cost 3 cents, something like that, right? So this is great. All right, so what did we do here? Again, we're evolving a compiler to make it produce compiler errors that actually tell you what's wrong, that you can fix. The way it works is we have a CY wrapper. It actually works for other languages besides C++, but C++ is a pretty serious pain point. So it wraps up a lot of information that it has because it's sort of hijacked the way the compiler works. So it has the command line info, which is important. For example, if you use some compiler flag for some language variant of C++, right, it's important for the LLM to know which one it is so it can understand the error and how to fix it. The error message, of course, we parse out the error messages on a language-by-language basis, so we can grab snippets of the code, and we form a prompt. We send it to the LLM, and like the previous systems, we turn the LLM into basically it's an agent, right? It can run something on our behalf. So we have these functions, like what was the command line used to compile or run this code? Give me some code surrounding it, list a directory so we can actually sort of navigate a directory and find the source code. The LLM can do this code discovery on its own. Like ChatDBG, we integrate a language server as well so we can find definitions. But here's a super fun thing that we also do. We extend it with a git command. And so the insight here is your code probably used to compile. At some point when you checked into the repo, hopefully, I have actually seen cases where people check in code, usually students, that doesn't even compile. Never do that. What are you doing? Right? Fix the problem first. So here it actually goes and allows the LLM to say, well, what did change? So you could have a huge code base, and you'll just have this narrow diff, which helps focus the attention of the AI. All right? And so, I showed you that demo. It works pretty well. I happened to be at CPPCon, which is a C++ conference, and this guy presented this talk on, it's the most C++ thing ever, effective compile time parsers. So if you're not familiar, the C++ community wants all the work to happen in the compiler. If it takes 20 minutes for the thing to compile, fine, as long as it runs 0.01% faster. And by God, I love that attitude. All right, so during his demo, he had a mistake in his code, and it produced the usual C++ raft of errors. And he was like, well, oh, I'm not sure what went wrong. And it's like, well, what do you do about these errors? How do you make it usable? And it was like, so I was like, oh my God, CY to the rescue. So got his code, ran it with it, and here is a case, again, where the domain knowledge of the LLMs really shines. It says, hey, you have this regular expression in your code, but it's actually invalid. So it understands regexes. So here is this library And here's whatever language-specific information you could imagine it might be able to understand, but it actually gets to the root cause of the problem. And this is a brand new library. The guy just released it at the conference, and the LLM was still able to reason about it without any training data at all. All right? And again, cost a couple cents. And I ran this by the presenter. He said, hi, yes, this is correct. It provided an amazing answer, way better than I expected. So, CY, compiler that explains the error messages and fixes them, again, exploits its niche. It has the source, of course, because it's the compiler, but it leverages a language server, which, by the way, language servers work well even for code that doesn't compile. So this is a huge win. And then its ability to exercise Git and drive the process of discovery of all the code. And ensuring the fitness is also straightforward. Obviously, you patch the code, verify that the compiler error goes away. Reasonably straightforward. It's a little more difficult to understand whether something is correct. Right? There's no oracle. Your code doesn't compile, and now it does compile. So validating it is obviously going to need something like continuous integration testing. All right, 2 more tools. So this one is Cover Up, evolving a new coverage tool. So this we also just presented at FSE. So I wonder how many of you out there this will resonate with. But there's this thing that some professional software developers do. It's called writing tests. Have y'all heard of this? Yeah, people are like, what? Tests? So they write some tests, and they're like, oh, I'm testing my code. Well, how do you know if the tests are any good? Right? Like, oh, my code passes all of its tests. Hope for the best? Right? I mean, yes, you could hope for the best. I put a couple tests in there. 3 tests. How many more tests do we need? Right? So there are various ways of trying to get at the quality of tests. There's a kind of hallowed way of doing this called coverage analysis. And so coverage analysis just means, look, when I run my test suite, how many lines of my code or branches in my code get exercised? Less is worse. More is more. All right? So in principle, you would like to get more tests. The more tests will drive up the number of coverage, right? If you have a test and I covered 50% of the lines, and I write a new test and it didn't change the coverage at all, it's not clear you did anything, right? So again, there's lines like the individual lines of code and then the direction of branches that get taken, right? So in principle, so you can have very high line coverage. You could have not high branch coverage. The ideal is probably path coverage, but path coverage is intractably large, because if you have a branch, there's 2, and it has a branch, there's 2, and their friends and their friends and their friends, and soon you have too many branches. All right? So the thing is that real test suites often fall very far short of 100% coverage. You might think, oh, that's got to be the gold standard, right? 100% coverage. Surely professional software has, the good tests, and those tests cover the code. This is an actual widely used system, and the line coverage is 38%. And I'm sure they're not thrilled about this, but this is actually pretty typical. So why? So the problem is testing code is hard. Why is writing software tests so hard? Testing is hard. Writing tests is killing my creativity and motivation. And then my favorite, writing unit tests is sucking the joy out of programming. So programmers basically hate writing tests. I have literally met one person, the graduate student on this work, who loves writing tests. No other person, and boy, getting my students to write tests, the other students in my lab, it is definitely like pulling teeth. But I get it. Right? It's painful, right? So wouldn't it be nice to have a coverage analyzer that wrote the test for you? And so that's what Cover Up does. So Cover Up actually generates tests that dramatically increase the branch and line coverage of code. So you might be asking yourself, well, wow, that's cool, but can't we just ask GPT for a test? So you can just give it a prompt and say, write me a test, and it will do something. And it does something. You actually can get increased coverage from 0, but it does worse than the state of the art. So that's not good, right? There is actually a whole line of search-based tools that actually go ahead and do things like fuzzing, or they do symbolic analysis, as well as LLM stuff to try to generate high coverage test suites, all right? So we built this tool CoverUp, and actually CoverUp achieves way higher coverage, higher than the state of the art, substantially higher than LLMs, and there's a couple reasons for this. So the obvious reason is CoverUp is better. No, the obvious reason is not obvious. It's that LLMs are broken in some way. LLMs are approximate, and they just, if you give them some snippet of code, they will hallucinate things. Like they'll be like, oh, you have this object A. I bet it came from code.models. Is code.models a thing? No, it is not. All right? So if you run that Python code, it will immediately fail. Here as well, the LLM is like, oh, I bet your constructor invokes something with an argument name X. It does not. But the LLM doesn't know, right? So the LLM can hallucinate this way. It can do worse than this. It can actually generate completely useless tests. So this one was pretty creative. It's like, I would like you to test A. Sure thing, boss. Here's a new A for you. And in Python, you can just redefine everything. And so this test runs, but it completely fails to do anything. So thank you, LLM. So what we need to do is we need to be able to tell the LLM, like, here's the information you need to actually produce like legit, reasonable code, and at the same time guide it to producing code that increases coverage. Right? So there's the sort of like avoid the bad and do more of the good. So we had previously built this tool called slipcover. Slipcover is a coverage analyzer. That's all it does. It's a zero overhead, basically near zero overhead coverage analyzer for Python, which is great because the previous tools were like 5x to 7x overhead. So 0 is a lot better than 5 to 7x. And so the way we start this process is we go and we use slipcover and identify the parts of the code that lack coverage. Right? Obviously, if our goal is to increase coverage, the things that are already fully covered, we don't need tests for that. All right? And then carves them up into segments. Then, our favorite trick, we use an agent. So we allow the LLM to call functions. And one of the functions, this very straightforward function, is getInfo. This allows the LLM to, with very little information, get a whole bunch of information back. So if it's like getInfo A, it'll come back and it'll say, here is the definition of A. Here's where it is defined, right? So it no longer has an excuse for just ginning up some random location or creating a new function or a new class. So then we have a feedback loop. So here we actually talk to the LLM. We take the code that comes back as tests. We run the tests with our coverage analyzer, which luckily is fast, so it makes this loop quick. And we then validate whether coverage increased or not. If it hasn't increased, we go back and we say, look, here are these specific lines that you've left uncovered. Cover them, please. So we can validate these, and we do this retry loop that increases the amount of coverage in lines and branches. And we do it up to 3 times right now. That seems to be the sweet spot. After 3, we get diminishing returns. Once we have the tests, we have to make sure that the tests are actually OK. Like, did they not just increase coverage? Did they run? There's also a really nasty feature here that we have to cope with, which is sometimes the tests will actually corrupt other tests. So my favorite one, it created a global variable. I'm sorry, it deleted a global variable. So it changed the global variable and then said, well, I'm done with this. And it just called del, which is a function you may or may not be familiar with in Python. But once you do that, your symbol is gone. And so this thing creates a test, and then it destroyed all the other tests. So you have to have some way of actually finding out what's wrong with the tests or isolating these bad tests so that they don't get included in your test suite. And at the end of the day, we save all the validated tests to the suite. So it works pretty well. So this is a comparison with the previous state of the art. And the green is cover-up, and the black is the previous state of the art. And you can see that there's a huge amount of mass in the coverage increase across all of these modules that we explored, thousands and thousands of modules. All right, so cover-up. Another example of taking a tool and evolving it. So we have a coverage analyzer that actually writes tests for you that increase coverage, eliminating the soul-sucking, creativity-destroying aspect of writing your own damn tests. It exploits a niche. Again, obviously it has the source code, but it can do static analysis of the source code to identify where definitions come from and what uses are of things. And of course, the key piece here is this dynamic analysis, which is coverage analysis, right? What are the lines that actually got executed? And finally, we can ensure the fitness, make sure the test suite is not destroying itself, and it actually increases coverage. All right, I'm going to close with our very latest and greatest tool. This is a different kind of software development tool. This is software development for basically non-programmers. All right? So how many of you all are familiar with computational notebooks? All right. There's a fair number who are not familiar. So does Jupyter ring a bell? 3 hands go up? OK. All right. So fine. I don't know. It could just be like, I'm a fan of Jupyter. All planets are great. So computational notebooks are these kind of cool things, but also kind of terrible. It's a web-based UI. And you basically get a Python interpreter, and you get little blocks. And then you can run code in these blocks. And it just shows you the result inline. So here's an example of somebody using pandas, and they read in some CSV, and it shows like a little snippet of the CSV to give you a sense of what's in the CSV. And then the next cell is an execution of plotting something, and there's the plot. So they're really great for rapidly iterating on things. It's a very convenient interface. It's also easy to share these things. There is some weirdness to them. So you can just move to any block that you choose. So you could be like, oh, execute block, execute block, execute block. Like, that seems reasonable. But you also can just go and re-execute a block. So you can execute things out of order. So the results are actually based on whatever order you executed them in. And there are these tiny little numbers that you can maybe make out that are by the side of the cells that actually correspond to their execution order. And things can get pretty messy pretty quick. So on the other hand, there's also this thing called ChatGPT or Claude or whatever, all of these LLMs that are pretty OK at using natural language to produce code to analyze your data set. So we gave some LLM this instruction, analyze this data set. And it does a pretty OK job. It comes up with some reasonable insights, maybe not perfect, and it generates a bunch of code. So on the plus side, LLMs can generate lots of code fast. On the downside, they can generate lots of code fast, right? Like, too overwhelming. They give you very little control over how the program is going to be formed. And it can be really difficult to verify that what actually got generated is correct in any way. So back to my favorite news source, Reddit. I'm giving up. I just want to say, I have to read this in a snarky tone. I think that this is the way it was said. I'm giving up on creating anything anymore. I was trying to create my little project, but every time there are more and more errors, and I'm sick of it. I'm working for about 3 months. I do not have any experience with coding, and was doing everything through AI, Cursor, ChatGPT, et cetera. But every time I want to change a little thing, I kill 4 days debugging the other things that go south. So I don't have any energy in me anymore to work on this. It is hopeless. AI is still just so stupid. And it will fix one thing, but destroy 10 other things in your code. I am really sad, because I was enjoying it in the beginning, but now it is just pain and rage. And I feel this person's pain. So the hope is we can somehow make things better, right? We have these LLMs. Let's harness them in some way that is still controllable and allows us to get verifiable code while also letting people who have no coding experience or limited coding experience be productive, right? So what we argue is we need a new programming model and a new interaction model. Doing this in notebooks maybe is not going to cut it. And when I say a new programming model, I actually mean a super old programming model. So here's a picture that we took of an actual data scientist whiteboard. And if you abstract this out, it basically looks like a data analysis pipeline. And so it says, load data, clean the data, wrangle the data, explore and visualize the data, and interpret the data. All right? And all the other stuff is details, like it's the implementation. So this is a data flow graph. All right? And so data analysis pipelines basically are data flow graphs. So we can actually leverage these data flow graphs to control how we generate code and ensure that the code that's generated is actually valid. And so let me dive in a little on what this means. So we built this system called Flowco, which we'll be presenting at WIST. And so you can actually try Flowco right now. It's hosted on Amazon servers. This is, rather than like we're going to have notebooks and you're the programmer and you fill things in and you just execute stuff, here LLM assistance informs every single stage of the process. right? So it's this data flow programming model that is going to enable us to get effective and reliable LLM-centric programming, specifically for this particular domain. So I'm going to just zoom in on a couple little pieces. So here is a view of a node. It says key means cluster, and you can see the output that's shown sort of like a notebook, a little preview. But in the middle, you see that it says requirements. And so these requirements are actually post conditions that must be satisfied by this node. And the requirements are all written in English. You can view them as code. The LLM will actually suggest the requirements based on whatever information it has from the data flow graph about all of the predecessors of that node and where the data comes from. And it'll suggest them, and the user can just click on a checkbox. Say, yes, this is a good requirement. This is a good requirement. If the requirement fails, then it will alert the user and say, this requirement was not satisfied. And then the user can, of course, go back and say, oh, maybe my requirement was too strong. Or, in fact, oh, there is a problem. My requirement is not being satisfied, and that's legit. Here's another view of output checks. So if I have a node and it's producing output, I can verify, again, the validity of these things. And you can ask it, as you can see, to suggest more possible conditions. And the LLM will go ahead and synthesize them and allow the user to vet them. It's also what's called in the HCI community a mixed initiative system. So this means you can do things in sort of different ways. So you can use this notebook and go ahead and place nodes and draw arrows between them. But you can also interact with your program directly via kind of ask me anything interface. So here you can see at the top left corner, it says requirements or code. So if you want to see the code, you can. You can operate at your desired level of abstraction. And then you can ask questions like, what is going on? Which cluster exhibits highest correlation? So you can chat with the program and with its results. You can even, in the chat window, say, oh, I would like a new node that does whatever, and I'd like it connected in this way, and it'll fix it up. One very cute thing I want to stress about the way that this all works is that not only does it go ahead and instrument these things with dynamic checks and all of this sort of stuff, but when it's synthesizing code, it will actually take a picture, a PNG-like screenshot of the graph, and use that to guide the development of the individual nodes or modifications. So this works great with these multimodal models that can actually understand images, often better than some like JSON representation. So again, in this template, here we have a notebook, but the notebook now requires no coding and also ensures a sane execution order. We exploit a niche. The niche here is really that when data and analysts work, they work in this implicit data flow graph. We make the data flow graph explicit and then use this to enable both analysis and validation. And we ensure fitness here, really getting a lot higher degree of rigor than you would get out of a notebook. This is all enabled, again, by this data flow paradigm and allows the user to not just generate specs, but actually validate the specs and have these things checked at runtime. So to wrap it up, I'm proposing that we all revisit our tools before they go extinct and harness the best of both worlds to evolve them, exploit their niches, and ensure fitness. I've talked about a number of projects. I hope that all of you will think of some new exciting ways to make this integration between AI and dynamic and static analysis tools a reality. Thanks for your attention.